Hello everyone, this is an audio lecture for visually impaired student, and in this lecture we are going to discuss about D and F block elements. D block elements. The D block of the periodic table contains the elements of the group 3 to 12, in which the D orbitals are progressively filled in each of the 4 long periods. In these elements, the last electron enters in n-1 d subshell, d orbital of the penultimate orbit, that is n-1 d subshell is gradually filled up. The configuration varies from n-1 d1 ns2 to n-1 d10 ns2. These are present between S and P block elements. The properties of these elements are intermediate between the properties of S block and P block elements. 40 elements belong to D group. 4th, 6th, 5th and 7th periods contains the 10 elements each. There are mainly 3 series of the transition elements: 3D series, 4D series, 5D series and 6D series. Transition elements. These are often known as transition elements because their position in the periodic table between S and P block elements. Typically, the transition elements have an incompletely filled D level since 12th group has D10 configuration and are not considered as transition elements, but they are D block elements. D block element shows horizontal as well as vertical relationship. Zinc, cadmium, mercury are generally not regarded as transition elements because they have fully filled orbital. Their configuration is: zinc have configuration 3d10 4s2, configuration of cadmium is 4d10 5s2, and configuration of mercury is 5d10 6s2. So out of 40 D block elements, there are 37 transition elements. All transition elements are D block elements, but all D block elements are not transition elements. Electronic configuration. General electronic configuration of D block elements is n-1d 1 to 10 to ns0 to 2. For 3D series, the configuration is 3d10 3d1 to 10 4s1 to 2. For 4D series, the configuration is 4d1 to 10 5s0 to 2. For 5D series, the configuration is 5d1 to 10 6s1 to 2, and for 6D series the general outer configuration is 6d1 to 10 7s1 to 2. Most of the elements possesses 2 electrons in the outermost orbital, that is ns2. However, some of the elements such as Cr, Cu, Nb, Mo, Ru, Rh, Ag, Pt, Au and Rg have 1 electron in the outermost orbital, that is ns1, while one element palladium has no electron on ns orbital. The irregularities in the observed configuration of chromium, copper, molybdenum, palladium, gold and silver are explained on the basis of the concept that half-filled and completely filled d orbitals is relatively more stable than partially filled d orbitals. General properties of D block elements or transition elements. Number 1. Variation in atomic and ionic sizes of transition metals. On moving left to right in the period, generally atomic or ionic radius value decreases. The atomic radii decreases from Sc to Cr because the effective nuclear charge increases. The atomic size of FeCO(Ni) is almost same due to increase in nuclear charge is cancelled by the repulsion between the electrons and increase in shielding effect. Copper and zinc have bigger size because the shielding effect decreases and electron-electron repulsion increases. The order of the size of 3D series is given below. The variation in covalent and metallic radius of Cr and Mn is due to the fact that in case of Mn, 2 electrons participates in metallic bond formation, whereas in case of Cr, 3 electrons participate in formation of metallic bond. Therefore, metallic bond strength of Cr is high and its metallic radius is low. Ionic radii. The ionic radii follow the same trend as the atomic radii for the same oxidation state. The ionic radii generally decreases as the atomic number increases in a particular transition series. The ionic radii decreases with increase of charge on the ion. For example, Fe3 positive have ionic radii 0.64 and Fe2 positive have ionic radii 0.7. Lanthanoid contraction. There is a regular decrease in the atomic and ionic radii of the transition metals as the atomic number increases. This is because of filling of 4f orbital before 5d orbitals. This contraction in size is quite regular. This is called lanthanoid contraction. The conclusion of the lanthanoid contraction is that the 4d and 5d series exhibit similar radii and have similar physical and chemical properties much more than the expected as the usual family relationships. 14 lanthanoids between La and HF. There is continuous decrease in the size from Ce to Lu. HF size becomes nearly equal to the side of Zr. Density. Density of these elements generally increases with decrease in metallic radii coupled with increase in mass. Thus, from Ti to Cu, the significant increase in density may be noted as order of density of 3D series is given below. In D block, OS and IR has highest density, and in 3D series, Cu have highest density. Ionization enthalpy. There is slight and irregular variation in the ionization energies of transition metals due to irregular variation of atomic size. The Le of 5D transition series is higher than 3D and 4D transition series because of lanthanoid contraction. Order of ionization energy of D block elements is ionization energy of 3D series is smaller than 5D and the IP of 5D series is greater than 4D. There are various exceptions in the IP of D block elements which is due to the following reasons. Exceptional electronic configuration, irregular variation in size and effective nuclear charge. When electron is removed from ns orbital, then remaining electron is shifted to n-1 orbital, due to which the number of exchanges are changed and IP also changes. On moving from top to bottom in D blocks, nuclear effective charge is a dominating factor. Order of IP of 3D series will be given as below. The order is oxidation states. D block elements show variable oxidation states due to tendency of n-1d as well as ns electrons to take part in bond formation, except 3rd and 12th group elements. Characteristic features of oxidation state. Sc and Zn don't show variable oxidation state. Most common oxidation state of D block metals is +2. Highest oxidation state of 3D series elements is +7, while those of D block elements is +8. Highest oxidation state of D block element is found in the mid of series. Stability of highest oxidation state is increases up to mid of the series and then start decreasing. D block metals can show zero oxidation state when a complex compound has ligands capable of pi acceptor character in addition to the sigma bonding. For example, NiCO4 and FeCO5. Highest oxidation state of D block metals is found in their compounds with oxygen and fluorine. The high value of oxidation state of above elements is due to very small size and very high electronegativity of oxygen and fluorine. Highest oxidation state of D block metals with respect to halogen is found to be +6. Moving from left to right, the elements having high oxidation states are less stable. For example, Fe shows +2 and +3 variable oxidation states. The relative stability of various oxidation states of a given element can be explained on the basis of stability of D when having no electrons, when D is half filled and when D is fully filled, means D0, D5 and D10 configurations. For example, Ti4 positive is more stable than Ti3 positive because in Ti4 positive, D shell is empty. Similarly, Mn2 positive is more stable than Mn3 positive and Fe3 positive is more stable than Fe2 positive. Magnetic property. On applying magnetic field to the substances, mainly two types of magnetic behavior are observed. Diamagnetism. Diamagnetic substances is one which is slightly repelled by the magnetic field. Paramagnetism. Paramagnetic substance is one which is attracted by a magnetic field. Due to presence of unpaired electrons, paramagnetism occurs. Each such electron having a magnetic moment associated with its spin and angular momentum. The magnetic moment is determined by the number of unpaired electrons. Magnetic moment is equal to under root n into n plus 2 Bohr magneton, where n is equal to number of unpaired electrons. If all electrons are paired, substance will be diamagnetic and magnetic moment will be zero. As it is evident, most of the transition metal ions have unpaired electrons in their d orbitals. Hence, most of the transition metals ions are paramagnetic in nature. Transition metal ions having 3d0 and 3d10 configuration exhibit diamagnetic nature. An unpaired electron spins, and as it is a charged particle, magnetic field is created due to its spinning. The magnetic moment of diamagnetic substance will be zero as the number of unpaired electrons increases. The magnetic moment created goes on increasing and hence the paramagnetic nature also increases. Transition metals ions having d5 configuration will have maximum number of unpaired electrons, therefore they will be maximum paramagnetic in nature. Formation of colored ion. D block compounds are generally colored due to unpaired electron result in DD transition. Charge transfer spectrum. Polarization. A substance appears colored because it absorbs light at specific wavelengths in the visible part of the electromagnetic spectrum and transmits or reflects the rest of the wavelengths. The frequency of light that is absorbed by nature of ligand, oxidation states of metal, and the size of metal ion. D block metal cation having paired electronic configurations are colorless, whereas those have unpaired electrons are more colored in nature. Transition metal compounds are mostly colored in their solid or in solution states. Charge transfer spectrum. Absorption and emission of light in d block metal cation having D0 or D10 configuration is induced by charge transfer spectra. For example, K2Cr2O7 D0 that gives orange red color, K2Cr2O4 D0 gives yellow, KMnO4 D0 gives purple, Cu2O D10, that is ruby red. Charge transfer is an example of redox reaction, and in charge transfer spectra the net oxidation and reduction is zero. Charge transfer spectra is divided into two categories. Number one is charge transfer ligand to metal, and second one is charge transfer metal to ligand. In charge transfer ligand to metal, charge on metal cation is high, whereas charge on neighbor atom is low. And in charge transfer metal to ligand, the charge on metal cation is low, while the charge on neighbor atom is high. The examples are given below. Charge transfer ligand to metal, example K2Cr2O7, K2Cr4 and KMnO4, whereas Cu2O is example of charge transfer metal to ligand. Formation of complexes compounds. By virtue of their small size, comparatively high nuclear or ionic charge, and availability of vacant d orbitals of suitable energy, these metals exert strong electrostatic attraction on the ligands. The species formed on interaction of metal ions form complexes because of the following reasons. Their size of cation is small, high effective nuclear charge, availability of vacant n-1d orbitals of appropriate energy. The structure commonly found in such complexes are linear, that is, coordination number is 2. Catalytic properties. D-block elements and their compounds are known to act as good catalysts as they have variable oxidation state. They provide a new path with lower activation energy for the reaction and form unstable intermediate compounds. The adsorbed reactants provide a large surface area for adsorption, which are finely divided metals on their compounds react faster due to the closer contact adsorption theory. Catalytic property is probably due to the utilization of n-1d orbitals or formation of interstitial compounds. Here are some examples of catalysts and their uses. Formation of interstitial compounds. Interstitial compounds have similar chemical properties as the parent metal but have different physical properties such as density, conductivity, and hardness. Interstitial compounds are neither ionic nor covalent. These are non-stoichiometric. Characteristic features of interstitial compounds. They have high melting points, higher than those of pure metals. They are chemically inert. They are less malleable and ductile. They are non-stoichiometry in nature and do not follow the common rule of valency. Interstitial compounds are neither ionic nor covalent. Cementite Fe3C is an interstitial carbide. Cementite used for making railway tracks. Alloy formation. Alloy is a mixture of two or more than two different metals. D-block metals radially form alloy due to almost same metallic radii. Size differences is less than 50%. Example: brass is an alloy of copper and zinc. Bronze is an alloy of copper and tin. The purpose of making alloy is develop some useful properties which are absent in constituent elements. Alloy containing mercury as one of the constituent elements are called amalgams. For example, sodium amalgam NaHg. Properties of alloy. Alloy are resistive towards rusting. Melting point of alloy is more than pure metal. Alloy of transition metal like brass and bronze have industrial importance. Also, ferrous alloys Cr, WMO and Mn are used for the production of a variety of steels and stainless steel. Some important alloy of transition metals are: brass is an alloy of copper plus zinc, bronze from copper plus Sn, that is tin, Melting and boiling point. As the number of d electron increases, the number of covalent bond between the atoms are expected to increase up to CRMOW family, where each of the d orbital has only unpaired electrons and the opportunity for covalent sharing is greatest. In spite of presence of 5 unpaired electrons in Mn, the unexpected low melting and boiling points is due to its complex structure. It is unable to form metallic and covalent bonds. The absence of unpaired electron in zinc, cadmium and mercury is responsible for its low melting and boiling point. Tungsten and mercury have highest and lowest melting points respectively. Along the 3D series, melting point increases up to the middle and then decreases. Order of melting point of 3D series is given as below. Now we will discuss about metallic character. Transition elements have relatively low ionization energy and have 1 or 2 electrons in their outermost energy levels. As a result, metallic bonds are formed. Hence, they behave as metals. Greater the number of unpaired d electrons, stronger is the bonding due to the overlapping of unpaired electrons between different metal atoms. Transition metals are good conductor of electricity and heat. They exhibit all the 3 types of structures FCC, HCP and BCC. Melting point and boiling points of metal increases then metallic bond strength increases. Strength of these bond increases as there are more number of unpaired electrons, hence greater the number of covalent bonds. Zinc, cadmium and mercury are soft in nature as they have fully filled d orbitals, whereas CRMO and W are hardest metals as they have maximum number of unpaired d orbitals. Enthalpy of atomization. D-block metals have very high enthalpy of atomization due to presence of strong metallic bond. In a series where we move from left to right, enthalpy of atomization is first increases and then start decreasing. Enthalpy of atomization is depend upon interatomic interactions. Some important compounds of transition elements: oxide and oxo anions of metals. The oxide of transition elements are generally formed by the reaction of metals with O2 at high temperature. All the metals except Sc from metal oxide, which are ionic, from Mn. With increase in oxidation number, ionic character decreases. Mn2O7 is a covalent green oil. Even CrO3 and V2O5 as well as VO2 positive salt. V2O5 react with alkalis as well as acids to give VO4 3 negative and VO4 3 positive respectively. The well characterized CrO is basic but Cr2O3 is amphoteric in nature. K2Cr2O7, that is potassium dichromate. It is an important chemical used in leather industry and an oxidant for preparation of many azo compounds. It is prepared from chromite ore, that is FeCr2O4. Step 1. Chromite ore is fused with Na2CO3 or K2CO3 in excess air. The reaction is as given below. 4FeCr2O4 plus 8Na2CrO3 plus 7O2 gives 8Na2CrO4 plus 2Fe2O3 plus 8CO2. Yellow solution of Na2CrO4 is filtered with acidified with H2SO4 to give a solution from which orange sodium dichromate Na2Cr2O7 is crystallized. Note, Na2Cr2O7 is more soluble than K2Cr2O7. Na2Cr2O7 plus 2Kc gives Cr2O7 plus 2 NaCl. Structure of CrO4 2 negative and Cr2O7 2 negative are given below. Sodium and potassium dichromate are good oxidizing agent, but potassium dichromate is usually used as primary standard in volumetric analysis. Cr2O7 2 negative plus 14H positive in presence of 6 electrons gives 2Cr3 positive plus 6H2O. Here are few examples of reaction involving oxidation by Cr2O7 2 negative. Chemical properties of K2Cr2O7 heating effect. Reaction with H2SO4, reduction with H2O. These are the reactions given below. K2Cr2O7 on heating gives K2CrO4 plus Cr2O3 plus 3O2. K2Cr2O7 on reacting with dilute H2SO4 gives 2CrO3 plus KHSO4 plus H2O. K2Cr2O7 on reacting with concentrated H2SO4 gives K2SO4 plus CrSO4 thrice plus H2O plus O2. K2Cr2O7 on reacting with water and 3 carbons gives K2Cr2O3 plus KOH plus 3CO. The next one is potassium permanganate KMnO4 preparation. KMnO4 is prepared by fusion of MnO2 with an alkali metal hydroxides and an oxidizing agent like KNO3. This produces dark green K2MnO4 which disproportionates in a neutral and acidic solution to give permanganate. Characteristic properties of KMnO4. KMnO4 form dark purple, almost black crystals which have same structure as those of KClO4. The salt is non-soluble in H2O. It has intense color and weak temperature dependent paramagnetism. Green magnetite ion is paramagnetic while permanganate ion is diamagnetic. Pi bonding takes place by overlap of p orbital of oxygen with d orbital of manganese. KMnO4 is good oxidizing agent in acidic, basic and neutral medium. Half-cell reaction of KMnO4 in different mediums are given below. MnO4 negative plus electron gives MnO4 2 negative. MnO4 negative plus 2H2O plus 3 electron gives MnO2 plus 4 OH negative ions. MnO4 negative plus 8H positive plus electron gives Mn2 positive plus 4H2O. The hydrogen ion concentration of the solution plays an important part in influencing the reaction. Although reactions can be understood by consideration of redox potential, kinetics of the reaction is also an important factor. Important oxidizing reactions of KMnO4 in acidic medium. These are following reactions. For example, Fe2 positive plus MnO4 negative plus 8H positive gives Mn2 positive plus Fe3 positive plus 4H2O. C2O4 2 negative plus MnO4 negative plus 16H positive gives Mn2 positive plus H2O plus CO2. S2 negative plus MnO4 negative plus H positive gives Mn2 positive plus H2O plus S. Now these are the some reactions of KMnO4 in neutral or alkaline solutions. MnO4 negative plus H2O plus I negative gives MnO2 plus OH negative plus IO3. MnO4 negative plus S2O3 2 negative plus H2O gives MnO2 plus SO4 2 negative plus OH negative ions. MnO4 negative plus 3 Mn2 positive plus